Hi, my name is Steve Souders. I've only been at Google about 4 months. I work on web performance, so if you have a slow website, you'll be running into me soon. I'd like to introduce Andy Hopper for today's Tech Talk. I'm going to do a little short bio. Andy got his PhD at the University of Cambridge in 1978 in the field of communication networks. As part of that, he helped create the Cambridge Fast Ring that had speeds of 100 megabits per second back in 1980. He's now the professor of computer technology and head of the computer laboratory. In addition to his work in the academic field, he's co-founded a dozen companies, including Acorn Computers and Adaptive Broadband. He's a fellow of the Royal Society and Royal Academy of Engineering, and he's also a fellow at Corpus Christi College. In 2007, he received the Order of Commander of the British Empire, CBE, which is a distinction held by fewer than 9,000 people at any time. He's married and has 2 children and has an airstrip next to his house in Cambridge. So he likes flying. And so without any further ado, Andy Hopper talking about computing for the future of the planet.
Okay, thank you. It's not, the airstrip isn't in central Cambridge, it's just on the outside. So number one, which is slightly complementary to this, we're having at the department, at the computer laboratory, a PhD show and tell to industry at the end of September. And I hope this is aimed at probably a small group of CTO types from industry, primarily. And so I very much hope Google will participate and send people who can interact with us and judge for themselves and recruit and talk the talk and interact with our PhD students primarily. And we have very good ones. And we're quite a big production line of PhDs, many of whom work in Google. So there's a little draft program, okay? What I'll talk about I've thought about for several years, having been exposed to the more conventional sustainability issues to do with civil engineering, water, that sort of thing. And so this perspective on how computing might have a role in the future of the planet represents a sort of assertive engineering approach to what is our place in all this and what we can actually do about this. So it's a framework, it's a perspective, and within that there are many, many projects which go on, and they can go to a level of detail which even the most professional engineer would find satisfying. But today I'll probably talk mostly about the higher level things, just to give you a flavor of this. And my own interests range from the more academic type of thing to business and P&L, and I'll cruise across this boundary and try and point out things that are a little more forward-looking, and then I'll mention 1 or 2 companies which are already doing some of this stuff, primarily in the Cambridge area, because that's the area I'm most familiar with. But it's all summarized over here. We believe that computing is a crucial weapon. It's the pacemaker of the planet. It will help optimize physical resources, and that the use of physical resources will be substituted by doing things in the digital world. And we also envisage that the developing world, population growth in the developing world, will be enabled, in other words, wealth creation in the developing world, in cyberspace, essentially, by doing stuff digitally. And I'll try and illustrate why I think that in my talk. So there are 4 categories of things that we think of. An optimal digital infrastructure, so that's your computers, your networks, all that sort of stuff. The notion of sensing the world and then optimizing something in digital space, which hopefully is more energy efficient than whatever you're trying to target, and then reacting to that. Thirdly is modeling the world, both short-term and longer-term, in a better way, so we are more confident in what might be happening. And finally, these digital alternatives to physical activities. Are we all going to cyberspace and are happy? Okay, I'll mainly talk about 1 and 2. I'll touch on 3 and 4, and then I'll summarize it. Okay. I won't go too wacky on biodegradable chips or recyclable computers. Those are thoughts. But I'll just be sort of much more down to earth, I like to think. So let's start off with, and I'll start accelerating in a minute and go a little faster. Optimal digital infrastructure. What do we think that might be? What are our perspectives on that? Yeah, one of the biggest operators of digital infrastructure on the planet here at Google. So provisioning appropriate availability is one thing, then energy efficient computing, and then finally our version of perhaps a slightly weird outlying overall goal in all this. So let's start off with provisioning appropriate availability and just start working up. So currently so I'm talking about server farms, the sort of things you have in tens and hundreds of thousands. Let's just take a look at what it looks like now from a redundancy point of view. We have the computer equipment, and we sort of start doubling and trebling and quadrupling up on the main supply, the uninterruptible power supplies, all that sort of stuff. And in many situations, certainly the ones I've visited, big data centers in the UK that are accessible to me, there is a large amount of support equipment which substantially increases the energy cost, doubles the energy cost. So we need to at least start off by reducing this redundancy, level of redundancy in this standby stuff in order to reduce this duplication, while at the same time improving the restart times of services, which can be about 4 hours currently. So that's a beginning. But we can move on. We can have a look at the actual data centers themselves. The data center is becoming much more of a programming problem rather than just have a duplication and start that up when appropriate. So we have this notion of adaptive, more programmable data centers, where we can observe what's happening in different modules of the data center and be able to recover from many, many more failure conditions, also have much clearer cut service agreements, boundaries for functions to be done. And in particular, we can start increasing the cost of energy, or at least accounting for the cost of energy in this stuff in more substantive ways. All in all, both in terms of the hardware support, the power supply support and all that, and also in the way you map some of these basic modules, processes, software tasks onto machines, we can start running closer to the wire, and that will be a good thing, and there'll be energy benefits from that point of view. In particular, we have a goal, which is to scale energy use throughout all this, actually throughout everything, all digital infrastructure. That's one of the sort of goals. With useful, emphasis useful, work done at all levels. And by useful, I mean it's doing something for somebody as an end user, essentially, not in standby at any level. So we'd like this energy use to be scalable in that sort of way. And we might wish to achieve that, to develop some principles which might be switch it off if not in use. That's a sort of more academic thing. Maybe low power is enough, but actually let's think switch it off, because switching things on and off causes computing problems. Don't send data if not wanted. It's a principle. We break that one all the time. Design better networking, know where traffic is coming from, the security, the energy cost of the security issues, spam, security problems, all that has a significant. And then in due course, perhaps we'll have to concentrate on whether photonics or plastics for displays or things like that, on technologies which are very good from the point of energy and scale linearly or even better. The faster you go, the more efficient it is, which is the case to some extent with photonics. So let's have a look at a single server, and let's have a quick look at the power utilization and the energy costs of a server. These are spec marks, new spec marks, energy spec marks, Xeon processor, and what we have here are 3 loads, and they're just different, but there's no meaning really between the 3. And on the bottom you've got utilization, and on the side you've got power in watts. So it shows you that the power consumption is several hundred watts, 200, 300, 400, not 400, 300 watts, 200, 300 watts when the thing is idle, so it's the power, and then unless it's being used a lot, if it's idle much of the time, then the actual energy use is even worse. So this isn't very good. It's not energy proportional because I'm not switching it off at this point. At 0, it's still using something. And it's idle quite a lot of the time. So we need to pack the jobs better. And this is, again, at all levels, this is a workstation, a motherboard, if you like. One of my students has been looking just at disk drives, the energy used in detail on a disk drive. Reading consumes more than writing, and you do 4 times more reads than writes. And you can, if you start factoring that in, the way you lay out a file on the disk changes. And even at that little level, you can get improvements. They're not going to double or treble your improvements. Maybe substantial saving, might be 10%, 15%. Actually, throughout the whole infrastructure, that might add up to something. So server consists of more than disks. So now if we've got a server farm, a multiple server situation, this is what things might look like. Along the bottom, I've got number of servers, again, power in watts on the left-hand side. The spec marks are the same, but now what I'm doing is showing, in each case, a red graph, which is the optimal situation, where we start using the first one up to 100% utilization. We switch in the second one, move across on that one, and so on and so forth, whereas the gray ones are the same size of clusters, so say 5, where you're not moving things around. So it's 5 times whatever the idle's utilization, energy utilization is at the bottom. Now, if we stop switching off machines that aren't in use, we approach the red line, and we start doing energy proportional computing. There's been an excellent paper from you at Google on energy proportional computing. So we need to move these tasks between machines. We might be able to delay some tasks so that we achieve the red route rather than the gray one. And there isn't much in the shape of these sort of things. So how can we achieve this? And it's getting there, so it's really not too bad. It depends what your computation, what your framework is. If you don't mind the applications knowing about this, then there's a technique called load concentration, which can assign the jobs to different machines, and you can get a 30 to 80% improvement. Something we're a little more familiar with in the computer lab in Cambridge is Zen, which is a virtualization system kernel, where you can move images around between machines. There it's the storage area network context, so the data copy is faster because you have that sort of assumption. And you can move tasks between servers in something like 250 milliseconds downtime, perhaps a little faster. This is on 1 gigabit Ethernet, and 60 seconds elapsed time. But with 10 gigabit Ethernet, the measured elapsed time is around 10 seconds right now, so it's getting better. So these are conservative figures. You can go further. And Zen Source was bought by Citrix. That's a Cambridge company, and SolarFlare is a 10 gigabit Ethernet chip company with physical layer a network controller, and the 10 seconds is on a configuration using that network controller. And you know, the numbers will keep on improving. And if we can go back to the good old days of almost batch computing, or we can categorize the different jobs between indexing, which is easily distributable, this is what you're able to do, simulation, so-called scientific computing, climate models, then the way you can actually delay these things and restructure the compute task is easier. So you know, it looks doable. We're approaching that sort of thing. So far so good. So far so obvious in a sense. Although there is engineering detail, and you know, depending on your data model, whether you're doing computing pi and that's what you're reloading, or whether you're taking your, you know, billion photographs and you're moving those around at 3 bytes per pixel and, you know, 10 megapixels each, you know, quite different. But nevertheless, so far so obvious, albeit difficult. So where can we go beyond that? So here is perhaps the little more forward-looking academic perspective. So what we can conceive of is not just moving the compute jobs to where the energy is cheap, which is something you in Google do already, on the premise that it's easier to move jobs than to bring the energy, but actually keep chasing the so-called sustainable energy around the world to where it's actually being generated right now, and quickly use up any capacity, energy capacity that's being generated that would otherwise be lost. That's the important point. So it's kind of free lunch computing because you can't use it for anything else, and yet you can move computing to where it's actually being produced. So on the left, windmill with a sun container full of servers, and there's a Siemens out in the sea, where it's easier to get a fiber optic cable to there than to bring the energy out. And the sort of research questions are, at what sort of granularity should these jobs be shipped? What is your data model? What do we should program? Data, both? What is the application? And these access patterns, the size of the jobs, the data collections, need to be modeled to give us an answer to those questions, which is one of the tasks being done by some of my research students, just to see how fanciful this is. But if it's actually not fanciful, then it will have two benefits. It will not just have a benefit in that the computing that gets done on systems where the energy would otherwise be lost. The other way around, the business case for putting up a system, say a wind power system, improves because now you can sell something, and actually the economics of doing it are potentially better. So it's, if it works, it's win-win. And this is computing. So let's now go a little bit completely crazy. If we were redesigning the whole shooting match, putting servers where that sort of energy is, could we do it? So this is a map of wind strength. Top is January, bottom is July. White is lots and lots of wind on average, albeit, of course, this is still going up and down. And you can see that you would want to put these windmills, in this case, where the white is. But there are variations. So remember, the question, do you ship it at 1 second, 100 milliseconds, 1 millisecond, 5 second, 10 second granularity? I don't know. But imagine the world's computing. So if you had some huge number of server farms, somewhere around here or whatever, and you just ship the stuff there, it's free lunch computing. And providing you account for the construction cost of the server itself and all that, the energy component of that, this might be a winner. So this is sort of wind related. We'd like to have a latency map of what it takes, a live latency map for the world based on this. Wind, solar is of course also important. And again, do you move things according to whether the cloud is passing or not? Good question. And perhaps even more sort of realistically, combined heat and power might become combined heat and power in any computing I can get hold of. So you put a computer with the heat and power plant, right, which is very mainstream. So you're generating electricity, you're giving off some heat, so that's giving you heating, but you also have a computer there which can absorb this sort of load, and all of a sudden, you've got another infrastructure you can place jobs on. And again, if that can be sold, then the business case for having a combined heat and power installation becomes more attractive. So you get an idea where I'm going here. Improve servers, make it more programmable, flexible, and then we end up with this overall goal. And the overall goal is, in terms of this optimal digital infrastructure, is, in the extreme form, switch off components that are not in use and achieve energy proportional computing at all levels. And then, if possible, do the computing, the energy proportional computing, in situations where the energy can't be used otherwise. That's the overall goal. And if computing, continues to, it's only 2 or 3% of any worldwide energy use at the moment, but if it ends up being 20% a decade or two from now, then this might be a way of dealing with it. And let's sort of invert this and say, what does it mean in terms of components, server farms, networks, workstations, and terminals? Well, I've mentioned what it might be in terms of server farms, redundant, adaptive, energy efficient, and then free lunch. The same thing can be applied, I haven't talked today about networks. You can switch off the networking parts and repackage networks so that the utilization is high, and switch off the ones that aren't in use. So, maybe this is time zones where it's dark, like in telephony in the old days. You follow the sun around the world and you redimension the networks. Workstations are banned in this thing because they're absolutely the pit, right? So we don't have workstations, they're centralized, so they're deleted, sorry, gone. And terminals are thin. So they're thin, stateless, and as low power as you can. And when I say stateless, that means you can restart them easily elsewhere. In other words, you can reconnect. It's virtualization, but the other way around. You can connect to your job wherever it's gone, rather than you running around. And of course, those should be designed in appropriate ways using, for example, some of the plastic displays that are coming along, which inherently, flexible, that sort of thing, which inherently are going to be very attractive low-energy terminals, low-energy consuming terminals. And companies like Plastic Logic in Cambridge are commercializing that sort of thing, or a company called VNC is doing the thin client stuff, which might be appropriate stateless technology that's actually widely used. Many of you, I guess, use that. Okay? So that's the end of section 1. And we'll see. Come back in I'd like to have a little more information about the way you run your server farms to compare this with the goal with one of the biggest installations on the planet. So maybe that will be possible. So let's go on to number 2, sense and optimize, okay? So, Google Earth, Google space-time, Google everything. Okay, so the idea is we have the whole world sensed up, modeled, and represented in a computer in real time. Everything that moves, everything. So the question is, how do we do it? Google Earth on steroids with spots on and on pot or whatever. But the proposition is, I remind you, that you sense, you optimize in the digital world, which has an energy benefit, and then you react to that optimization, at least by publishing the data, or perhaps more than publishing, controlling something. So here are the sort of things that you have to come up with, but on this huge scale. Okay? So the sensing itself. In my group, anyway, we're not particularly gang-ho on ad hoc wireless sensor networks, although we're very keen on managed and properly or fully engineered sensor networks. So one of my students, Bo, ALM Onono from the Cameroon, has designed a microprocessor architecture which has got this energy proportional computing stuff, but for the sensor part of it, and is reasonably scalable. Anyway, so sensing is important, and also how do you publish the data? How do you again, to give you a thought process here, if it was possible to know what everybody's car satellite nav settings are right now, just because it was you put it in, you say, Marriott or whatever, and it's broadcast. That would be a publication of data which a transportation system could use to then optimize something, right? So that's what I mean. You sense, and then you make the data available, and that's a little instance which could be done right now, basically. And then all these lovely, lovely problems. How do you make a world repository? What are the computation models? Where is the data? Where is the computing done? All the traditional sort of thing. How do you index things? How do you make it to spot things and generate events? And then how do you interpret all that? Not just observe and react, classify, optimize, but predict something and hopefully do something good as a result of that. Now, in Cambridge, both in the university and various companies, we've been immersed in this sort of sensing indoors for years and years and years. You may recall Xerox PARC had a project where they wore badges, and one knew where people and equipment were, active badges. Well, I sold those badges to them, and we've had them in Cambridge since 1989. So in terms of indoor location, there is a tremendous, 100 people have lived this for many years. So the world model outside is kind of inspired by what we can do indoors. So another company called Ubisense has a product, an indoor fine-grain precision location system, whose precision is about 10 centimeters most of the time, based on active tags, little tags you wear with a battery, and ultra-wideband as the time measuring component to give you the location. But just to give you a little flavor of what would have to be repeated on the world scale, I'll show you some of the things we do on the inside, building stuff. So top left is a picture of the real world with people wearing sensors, wearing tags which are being sensed, and all the digital infrastructure being monitored as well. And here is this, and put into the world model for indoors. And then here is a visualization, a synthetic view of the same thing. And if I plug you the video, all these people would be moving around, and things would be changing color according to the digital status of that equipment. So achieving good coverage there is itself problematic. And then you can start interpreting that world model, just to give you a little flavor of this sort of thing, what you might be able to do on the world scale. So this is a room. The yellow things are sightings of a tag in different places. And you can start doing algorithms which, for example, observe whether the tag moved from one square to the left or up or down, a linkage diagram. You can prune that tree, and you can end up with representations of these sightings, which are like this, which sort of indicates where people might have walked. The table may or may not have been scanned in or observed in some other way. So interpreting this world model on a world scale rather than indoor scale is interesting. And making sure it's right and up to date is another issue, consistency and dependability. So here is a room. This is a picture of a room where a table has been moved from the middle of the room to the side of the room. And because you got sort of side effects of the location systems, you can pick up inconsistencies and bring them to the attention of the appropriate authority, sort of autonomic computing. We've been doing some interesting work on outdoors as well. It's mainly based around the notion of a sensor car. So we've had this sensor car for several years now, and basically, I don't know, when you recruit in Google, do you show that, and then when you turn up, you get one of these? I don't know, that's the way we do it with PhD students. You say, you come and work on this project, that's what it looks like, but in practice, it's a van. Anyway, it's got all kinds of networks, so it automatically dumps stuff, and in particular, it's got sensors, camera out, camera in, pollution of various kinds, of course, GPS, all that sort of stuff. So that's our platform, which we sense Cambridge, basically, and throw things in. But towards the future, we'd think, for example, of the digital phone infrastructure with sensors on those digital phones as something that you could have worldwide fairly quickly, possibly, because the backbones exist, feeding into a federated, in other words, an open, a public, in some sense, global repository. And here are some results from the outdoors that we've been doing. So this is mapping the spectrum. Just to give you a scale, this is Cambridge, and these are roads, and the different colors represent 3G signal strength and coverage. So it's a map of 3G coverage. And when the car turns up, because it can be quite a lot of data, this is all uploaded to the repository, and we have that. And yet another Cambridge company, CRFS, is doing the hardware which actually will put in, again, a countrywide, but in due course perhaps global, spectrum sensing system for at a cost which is possibly affordable more generally. We mustn't also forget humans as sensors, because all very well this automation, but that's not the only thing. Much of the planet, particularly in the developing world, may be covered by human sensors. And here are some examples of the sort of thing that's been done. This is a human sensor, in other words, put in by hand map of Cambridge, and you get different kind of information about the pub in this sort of map than you do in the Ordnance Survey, our sort of mapping agency. And perhaps being able to do this in the developing world, use human sensors, in other words, with the appropriate incentives, will help us have a global repository which doesn't just incorporate Google out here, but elsewhere. But how to make the data consistent, how to have perhaps voting systems or reputation systems to make sure that this sort of thing, which is done jolly nicely by some group of people in Cambridge, actually scales as a human sensor system worldwide. Who knows? Here is something that I think is a little more specific, albeit a huge project for the future. So in one of the London boroughs, the London borough of Haringey used an aeroplane aerial survey to produce infrared maps of streets. And most energy goes through the roof from heating countrywide. So if you can observe that, maybe you can influence. Actually, it's who's growing pot is the it's perhaps the application, because maybe it's in that house there or whatever. Anyway, never mind all that. So this is an example of one of the layers that might be shown in a series of layers that interpret and present the world model to you. And there is an interesting question. What would happen, I would be an enthusiast of this, if this sort of data was made available and people could write whatever applications they want. I think that would bootstrap it up substantially. Now let me just say a few words, because it's important and unavoidable, about the ethics, the security, all this sort of stuff. So first of all, I'm assuming that if this goes forwards, we will measure whether individual behavior is affected by the data being generated and presented. And let's assume that from an engineering point of view, we're designing out the dangers is done sensibly. There are control mechanisms, gates, and the failure modes are taken care of, both in the sort of straightforward sense and the indirect sense. Now, this picture is of a queue for voting. In South Africa some years ago. And the question is, why do we queue? Why do these people queue up? Why do they choose to actually do that? And what does that tell us anything about the dilemmas that what I've talked about presents? Because this sensing observation reaction is Big Brother on the one hand, but on the other hand, it might be positive. So there are various dilemmas. I helped write a report for the Royal Academy of Engineering on this topic. So there are value dilemmas, which are between what's valuable for a community versus what's valuable for an individual. There are privacy ones, which are things like control versus convenience, anonymity versus crime prevention. They're dilemmas, and we make our call, but it's not all one way or the other. Dilemmas of the stakeholding, so privacy versus efficiency, and governance, in the sense of, is it a business model driven thing, market driven thing, is it a non-market driven thing, diktat driven thing, legal thing? Again, so there are dilemmas, and I'm very keen to communicate with the average person, so to speak, the man or woman in the street, to present this thing and at least have a view. And on this Big Brother issue, what is this surveillance scenario? At the moment, it's a big mess, right? It's who knows what it is. You can think of some of this as being Big Brother, but on the other hand, actually, part of the issue might be that we're big brothers of each other, that it's the citizens themselves. When you take a mobile phone photograph, you're being, in a sense, a big brother as a citizen yourself. One principle, as a result of all this work we've done with the indoor location and knowing or having data which indicates about where people are, is that this notion of reciprocity, watching the watchers, is key to this, that It's very important to put that in. What I can do to you, you can do to me, right? Everything else has to have special permission, but providing that's the case, actually, at least in the benign environments that we've worked this, it seems to be okay. All right? So that's this sense world model optimize. So let's just move on briefly to the predict and react and cyberspace. So predict and react, if I could remind you, that's about essentially using computer power to optimize something and then optimize the energy. And I'll talk just briefly about shorter term and then longer term stuff. So in the shorter term, another Cambridge, forgive me about all this Cambridge, but that's the world I'm familiar with. Camvid is a company that does routing software. And, at the moment, so it tries to know what's going on, where the traffic is, at least where the roads are, and does your routing. And you know how irritating it is at the moment. If you want to change the route slightly, you can put an intermediate point and another intermediate point, and it might take it, and you don't quite understand what's happening. And then any kind of perturbation in data, you don't have that normally too much, but you will in due course if you have road charging or carbon data from, there'll be perturbations in the data, which means those algorithms, current algorithms, are problematic. So what these lot have come up, Alan Jones and his colleagues, is a set of algorithms which give you, for any two places, the substantially different routes that are available and are not too sensitive to perturbations which might be as a result of some kind of carbon charging or carbon measuring or some measure like that. They build a tree out from each source to each possible destination. They build a tree out from each destination to each possible source. They overlay those two, and it turns out that you get plateaus of maximal overlapping of those trees, which turn out to be the substantial different routes. Brilliant, absolutely super. But going forward, it's exactly what's necessary to make the average consumer understand what's happening with road pricing or carbon in terms of their choices, their real just choices. So that's predict, react in the shorter term. And predicting, react in the longer term, meaning more substantial computing, looks something like this. So this is the current worldwide standardized, this picture, weather-related infrastructure, where there are standards, measurements are taken to a standard, computing algorithms are agreed, and those charts, synoptic charts we get, are produced on a rotating basis in 3 centers around the globe. So that's a good example. But actually, the so-called scientific computing, by and large, in my humble opinion, has not encompassed the best computer science principle. It's been mainly concerned with the result and how to get there and throw more computer power with it, rather than how the computation is done. And so I think we need to at least improve, possibly restart on these so-called scientific high-end computing tasks, which might be predicting global warming, for example, in order to make sure that the underlying things are accurate and correct in terms of the model, in the formal sense possibly, that they use the latest data, and in particular, work to a deadline, not just finish when the time comes. So for example, an application that we think of might be in the computational ecology area, where you've got bird flu, for argument's sake. You've observed it here. You've got some model which is running where it might go, and then you get a new observation, and you can't ignore that. It's happened, right? So it's no good carrying over that computation. So you've got to have a quantization of the applied mathematics, for starters, let alone the computing tasks, in order to take that in, okay? And then, of course, I want to run all this on the kind of infrastructure I talked about earlier. So I can accelerate time, the computational tasks, bring the results sooner by throwing it at server farms of the type I've described, but in an energy proportional way. And the last one, digital alternatives to physical things. So this is a lovely chart, which is in the computing chart, is a ecological footprint chart for different continents. So on the left, the scale is hectares per person on average in terms of the ecological footprint that's being used, and the biocapacity, I'm told, in equivalent units. And you can see that we, in North America, Western Europe, up here. So how do we deal with this? How do we, especially in the developing world, make it possible for them to have higher standards of living, but without causing that sort of footprint? So maybe it's life in cyberspace. So this slightly rhetorical slide, it ends up saying good news or bad news. So we've gone from physical to digital in a number of many things. So when you buy music these days, you do it digitally. You don't tend to go and drive to get the plastic, to get the CD, to come back. You download it. That may be good news. I'm not absolutely sure. I'm not sure. I'm going to try and have a view on this. But say whether it's buying CDs or doing shopping or electronic media, the newspaper online, there seems to be the possibility that there is more wealth in cyberspace. How might we calibrate this? So here is a sort of flagship thing, which one might wish to do. And I'm looking at this from a real hardcore computing point of view, but we would like to have a personal energy meter, which tells me how much energy I'm using, both direct and indirect. That's the galactic goal, right? So my proportion of leaning on this lectern here, there'll be a tiny little energy cost because I've used it a little bit. Let's go extreme. Now we can try and approach that and measuring things, all traditional stuff. And I'd hope that by being able to present to users what their true personal energy uses are, direct and indirect, we would at least have an effect on their behavior. And of course, we'd want to break it down into different things. There's a lovely effort, open source effort in the UK called Carbon Hero, where they basically use location information about mobile phones. They work out whether you're on a train because if you're doing 60 miles an hour and it coincides with a railway line, you're on a train, so that's your energy cost. So they give you an attempt or a figure which is an attempt at your personal energy use. And even if it's not far out, actually just getting people to think in that way, I think is hugely important. But from a computing point of view, again, it's a lovely, lovely set of challenges. Research, pragmatic, engineering, theoretical, all kinds of stuff. Because I want to upload my own use. I want to incorporate all these things and their energy component for this measure. I want to index it, cache it, all this sort of stuff. A little bit of prediction. Security, privacy, and possibly, social networking is very popular now, but I would like to participate in a social network which affects me one way or the other as a result of these readings being shared or talked about or whatever. Peer review, peer pressure. And now if you fast forward to the developing world, were they to have such a thing, again, that will inform the choices about the sort of infrastructures they build, because if you drive a car and it goes down the road and you account for the road, you account for the car in terms of energy, and you compare that to doing the equivalent thing digitally, it may be that this influences, is a method of accelerating the cyberspace version of some of this, informs the cyberspace version of some of this in their choices as you go forward. So we'll see whether we can shift to cyberspace in some substantive way on an ultra-cheap platform that everybody around the world has, with minuscule power, and so on and so forth. The pragmatic issues today are just, and you've just announced some stuff about sharing data and being kind of the middle ground for some of the social networking activities and profiles. So how to scale up virtual worlds is one of the sort of main things going on right now. So I'm almost finished. In summary, the computing for the future of the planet perspective is the proactive engineering context within which I, my group, my department, and I hope many others will do their projects. It tries to list and dimension the problems and set numbers to them. For example, you can do a back-of-envelope computation and work out how much data it would take to represent the whole world for everything, and that's doable. I think to the general public, it may be a good way of presenting what we do, because at the moment, energy use isn't desperately high, but it's growing. And at some stage, we might be surprised by a more critical perspective on us. And this is a good way of indicating, representing, why we should exist and why we're important. The National Academy of Engineering has published some of this, and Google participated, and it did have a lot of press. I'm very pleased to that. But this is the most important comment here. This whole thing contemplates the unbounded upside of computing, right? You can only build a certain number of roads, so to speak, but computing, the digital, the virtual, is essentially unbounded. And the changes, Google 20 years ago, not existing, just the very first indexing systems really being done. Think forward 20 years, it's unbounded. So it may have substantial changes there, and I hope I've given you a template for those. And this, finally, thank you very much, is part of the motley crew. But this is, these are some of the faces, including my daughter and my son, but that's just by the way. And at the other end of the spectrum, top right, Professor Sir Maurice Wilkes, who is head of the department in the past, was head of the department in the past, and still comes in many days and tells us whether he thinks what I've talked about is sensible or not. Thank you very much. Questions, comments, disagreements?
A question. I like your idea of the sort of dynamic computing following power. On the other hand, wouldn't you think that we would, first of all, it's to some extent that's happening already, data centers being very close to power, but you're obviously thinking more dynamically than that. But wouldn't you do better, actually, if you had distributed power generation as well? Have you thought about how the two go together?
Which power generation?
Distributed.
Yeah. Okay. So that's what I meant, combined heat and power. Look, so the academic perspective is, let's take this to the limit. Let's switch it all off, and let's see if we can have a single windmill, which is so big, it's completely out of the way, drives the world's computing power. Now, that's absurd, but it's an endpoint of the spectrum.
Google Chile looked like from the wind map.
Yeah, exactly right. So that's fine. And our PhD students will look at that, and we'll have models, and we'll have a comment on it, as well as wonderful PhDs. Reality is probably going to be one step back from there, but I don't know quite how far this might go, because it is back to centralization, back to that sort of stuff, and in many ways, not just energy, just making the stuff work, right? Dealing from a professional point of view with the infrastructures, that might be a good idea. However, in practice, it's going to be an evolution, because actually this is going to end up as product, and you're going to say, I'd be surprised if it's diktat. I mean, unless the whole global warming scenario goes completely nuts, bad nuts. It'll be, here is a bit of software which rearranges jobs on a farm, and here's your immediate return on investment, Mr. Customer, because you're going to save some energy, please. And they'll say, yes, thank you very much, I buy that. Maybe there'll be some regulation which says you have to have at least an audit trail, you, the company, of how you use energy before, say, the government of California, the state of California, buys from you, for argument's sake, just sort of another version of the, standby power kind of perspective. So I think it's likely to develop somewhere in between. Whether combined heat and power provides enough of a fiber, I don't know. We'll see. Probably.
But I was just thinking in terms of you seem to be focusing on centralization of computing rather than distribution of energy. And so, for example, when we say workstations are bad, well, workstations are bad only if they're drawing power from a central grid. But if they're drawing local power, let's just say I've got a solar rooftop, then maybe better off.
I certainly want to use up all the energy that can't be used elsewhere, and there will be many situations where the energy cannot or won't or just doesn't make sense to be transmitted out. For the heavy stuff, it probably does make sense, and my energy friends will say, we can put in a big energy cable. What's your problem? And it's a hugely huge pipe of energy. And I say fine, but I'm trying to find space, and I think we found space to evaluate where the role of this computing, which is unique in terms of chasing the job, and how it finds out, and that will have a place. Now, I don't know exactly where it'll end up.
Well, I don't want to monopolize the conversation here, but I was having a conversation with a VC who's making energy investments right now. We're talking about solar thermal and the fact that obviously it's appropriate only in certain locations, and those are not necessarily locations that there's lots of say computing right now, but you could theoretically say put your server farms down in the southwest where solar thermal makes sense.
Yeah.
And so that would certainly.
Yeah, so that's in line.
The biggest challenge is not actually generating the power; it's getting the power to where it is.
Yeah.
So your point of
Yeah.
computing is.
Yeah, and remember, I'm making the point both ways. And for having power being the person who puts, there's a small West Coast Scottish island where they've got this wonderful windmill, and they have 50 homes there, and they're saying they're ever so green, but actually the cost of all that in energy is much worse than having a very efficient diesel generator. Yet, if you have this sort of stuff, it actually might be that the true cost, if they can export energy services, computing services using the energy is business-wise more sensible. Any other disagreement? Mainly disagreements. Go on.
So I talked to engineers at other big companies, and there's a lot of interest and work in addressing that difference between power consumption of idle servers versus off servers. But if I read it right, one of your bullets said that power curve is less important for large server farms. Can you expand on that?
The proposition there is that you can more easily map the load onto the resource you have, just because you've got more servers and more jobs, which as a proportion of the compute resource you require are smaller, and therefore it's just a easier smoothing function, if you like. Any others? Sir?
I agree with a lot of what you said, of course. I'd like to talk about these issues. One thing that I wonder what your perspective is that a couple of things you mentioned sort of bump into this locality issue, right? One of them is, having sort of standby servers, maybe with very thin clients in which all your data is in this sort of centralized storage system that makes it convenient and very easy to turn things off. Sort of a little bit brushes over the fact that locality is actually good, right? People do that and they use that because it gives you performance. And if you actually store your data in a centralized place, you sort of destroy locality, right? In a way, and you have to do an infinite bandwidth storage system and infinitely fast networks in order to get your performance back. And the same might apply as well for the idea of distributed computing around the world, right? In the sense that yes, to some extent, I absolutely agree that computing is cheaper than sending some physical things around the world, and yet it's not completely free.
Yeah.
Right? Because of locality issues as well. Because your data is heavy somehow as well because the pipes are thin.
Yeah. Okay. Well, there are, I'll criticize myself if you want. That's all right. So there are potential flaws in this. I don't know. It may be that the true energy cost by the time you shift the data isn't that much better. So that's flawed. Or the performance doesn't work because you're too distant from the computes, and therefore the network actually isn't fast enough. Or in the digital space, in the cyberspace, you could say a webcam makes you travel more rather than less, right? So I know. So flog. However, in terms of intellectual perspective, there is a line. More pragmatically, on the thin client stuff, I just divide it up into, realistically, I say thin client to me means stateless, so I can restart it and redo it. But I might have all sorts of graphics and visualization, all sorts of local state, which is for the purpose of performance, and I might cache all sort of, and that's rather different. So I think of stateless, but for all sorts of reasons, when I need it, I might wish to have local thing, which might even go, to having some of the compute tasks closer. But, discuss. One of the things I had is latency map, and how does this work? Does it scale globally? And that's, that's exactly the sort of thing I'm trying to get a field for, and it's sort of the boundaries of the problem. Reality is going to be probably somewhere in the middle, but yeah, so, But also, you folks are very confident in this company, but you don't do physics, right? So for example, displays will change. The way we have terminals with flexible stuff, and the way we are presented with data will continue to change. And so that's another interesting perspective, exactly how we take advantage of the new physics, the new semi-plastic, all that sort of stuff, which will kind of affect this. Any other folks?
One more question. On your sensor, this idea of sensors and so open source data sharing of sensor data. I think I mentioned there's a new group called Optimise that's trying to actually do exactly that. The people that you mentioned, was that just an idea, or is there somebody working on creating that open source sensor data exchange?
Well, sensor networks have, as a concept and as sort of initial experiments, have existed for a long time. So, there are all sorts of things. The most complete thing, I think, is this human sensing and maps, actually, kind of thing. We will see which one of these activities scales. But, in order to, this is serious. This is not, the perspective here is we depend on this. So the way the data is collected, what the sensor was it calibrated, was it timely, what's the provenance of the data, is it a true data or is it a phony one? To do that properly requires some serious coordination. So I think it's early days, and all these efforts are great. I mean, it's wonderful.
Yeah, I think my point is right now, a lot of people are collecting data, keeping it private, a lot of duplication of effort. There's some open source efforts. You mentioned OpenStreetMap, but I think it's an important idea, this idea of open source data sharing.
No, absolutely, yeah. I mean, in the UK, we got all sorts of curious things. You're rather better off here in the United States. So even things like the Ordnance Survey map data is you have to pay for that, let alone anything fancier. The culture there isn't to make that possible. Again, we'll see how this turns out. One of my former PhD students did a project, a PhD, where the answers to the questions of how was it sensed, what was the object interface out from the module, was very computer science approach. So you had modules, you could place them all over the place, you could export data, the data was defined in the interface, so it was very computer sciencey kind of thing. Maybe that's one approach to standardization of this. You have at the other extreme just raw sort of sense of facts plus a little bit, basically a number plus something about what it might have been. It's early days, but I agree.
All right, Andy, thank you very much.
Thank you very much.